All right. Hello, 2021 Lafayette Motorsports team. I'm John Abel.
Hey guys, my name is Jordan Brosmer.
My name is Mike Ripmaster.
My name is Simone Khalifa.
Hi guys, my name is Tim LaGreca.
My name is Zach Miller.
Hi, I'm Lisa Caban.
My name is Dan Becker.
Hi, my name is Feng Qiu.
My name is Gabe Fagan.
My name is Noah Enjame.
Hi, my name is Montserrat Mendez.
Hi, my name is Leah Diamondidis.
Hello, my name is Nick.
Hi guys, my name is Maureen McShane.
Hi everyone, I'm Catherine Neely.
Hey everyone, the car team. My name is Philip.
My name is Luke D'Andrea.
Hello, my name is Tony.
Hi, my name is Austin.
Hi, my name is Dwayne Whitaker.
Hi, I'm Clement.
My name is Jordan Brosmer. I was the project manager. I guess I'm the MC kind of this Zoom call. But yeah, we're just going to talk about our progress this year, what we did this year, and all of our achievements, as well as obviously the downfall of the COVID-19.
So I'm Catherine Neely. I'm the other project manager. So the Lafayette Motorsports team is a group of undergraduate seniors who study here at Lafayette. The team involves 13 electrical engineers and 12 mechanical engineers who joined together in this class for the interdisciplinary project, demonstrating the experience gained by the team throughout our past 4 years here. Our faculty advisors for the 2020 team were Professor Nadovich, an electrical Professor Helm, a mechanical engineering professor, and Professor Sajadian. So the class of 2020 team had the general goal of making it to the FSAE Formula Hybrid Vehicle Competition, and our team heavily used the materials and worked off of a lot of the progress that the 2019 team made last year.
So our basic goals when we were making this, or when we were making a car, was that we wanted to finish the competition events, obviously. As we went into the year, we changed our mind a little bit, and the events became less important, and finishing the car became more important. We had to go through 5 events. For anyone who's unfamiliar with the Formula Hybrid event: project management, engineering design, acceleration, autocross, and endurance. They offer bonus points as well during the year when you submit. This is basically our full design of the car. It has all of our different subsystems on it, all of the things that we're going to be talking about today, including Carman, drivetrain, all of those things that we're going to be getting into more detail in the future. Each of the subsystems is going to be going into a bit of a 1-minute intro into what the subsystem is, why it falls into place on this car, and why we need it. And yeah, I'm just going to get started with that.
Hi, I'm Clement. I'm a senior ECE, and I worked on the battery packs. So, what is a battery pack and how does it fit into the car? So a battery pack is a device that contains multiple electrochemical cells which store large amounts of energy in a chemical form. And we fit these electrochemical cells in a garolite and aluminum container, which is secured to the car's chassis. They're vital to the car as they provide the motors with large amounts of voltage and current to accelerate the car forward.
Hi everyone, my name is Tim LaGreca. I am a senior mechanical engineer, and I was the lead mechanical engineer for the TSV subsystem and the battery packs. So some of the biggest accomplishments we had was, one, we had a brand new design for a very successful enclosure. We were able to increase the power to weight ratio. We have a very compact enclosure.
Hi, my name's John. I'm a senior. I worked on the battery packs as well. Some additional accomplishments: we completed a new design of the AMS. We eliminated segman board.
Hi everybody, Connor. I'm a senior EC. I did some work on the battery packs. We were working pretty hard to get the active balancing circuit working.
Hi, my name is Simone Khalifa. I'm an electrical engineer. I worked on the battery packs and focused on firmware. So something that we adopted was a CAN-open library, and the reason behind this was to standardize the system and be consistent with the CAN-open system that was used by the motor controller.
Hello, my name is Dwayne Whitaker. I'm an electrical engineer on a car project, and I also help with the CAN-open library.
Hello, my name is Nick Steele. I'm a senior mechanical engineer as part of the interconnect team. So the interconnect subsystem kind of contains a lot of smaller subassemblies, which we'll talk about throughout the presentation. The largest is Carman. Carman stands for car manager, and it contains a large portion of the electrical subsystems on the car. You can kind of think of this as the brain of the car. It contains the TSI, which we'll talk about in a bit, the relay board, which relays power from the batteries to the motor controller, and then the grounded low voltage systems as well. This sits on the back of the car and faces outward. There's 2 displays on the car that you can see: the SCADA display and then a voltmeter as well.
Hello, my name is Feng Qiu, and I'm a senior ECE as part of the Tractive System Interface Group. So I'm going to introduce the TSI board, the Tractive System Interface board, as part of the Carman. It is located inside the Carman enclosure at the back of the car. The TSI board provides a variety of functions to support the car. First one is the drive state. So according to the rule, when the car first power up or shut down, it must follow a sequence of procedures. So the drive state monitors that. And during this process, it also generates a lot of signals and lights like relative drive sound or tractive system active light. The TSI board also monitors a bunch of data like the battery and motor voltage and current, and it also measures the cooling system temperature and flow rate. It will report these data to our data collection system, SCADA. And lastly, one of the most major goals is managing the pre-charging and discharging.
My name is Noah Enjame. I'm a senior ECE, and I worked on the grounded low voltage system. And here we're going to talk about the grounded low voltage breakout board, or GLV Bob, which is also housed in the Carman. So the GLV board does a few things. We house relays for the shutdown circuit, or as we refer to it, the safety loop. Our board also supplies low voltage power to the vehicle, and we also interface with the data acquisition system, also known as SCADA.
My name is Michael Rittmaster. I'm a senior mechie, and I worked on the drivetrain system. The drivetrain is a subsystem that takes the torque supplied from the motor and transmits it to the wheels while also applying a gear ratio to make the system perform more efficiently. Without the drivetrain, there would be no car movement, so it's pretty crucial to the overall performance of the vehicle. I like to look at the drivetrain as sort of the bridge between the electrical components and the mechanical components, taking the power supplied from the battery packs and transmitting that into rotation. So in the image, you can see our exploded view of the drivetrain and some of the major pieces being the motor, the differential, the sprockets, and the half shaft.
Hi everyone, my name is Leah. I'm a senior ECE. So this is the dashboard, which is located exactly where you would expect a dashboard to be in front of the driver. I've focused on the dashboard display, which is mainly portraying information to the driver, things that they should know that could either cause the car to shut down, other warnings and things that they should know that maybe they should start slowing down. So that's all focused on the left side panel. So there's a display that shows both the speed and the state of charge of the batteries. There's two LEDs, one for the motor temperature, one for the motor current, and those are RG LEDs, so they can do red, yellow, green. So it's kind of a relative temperature or a relative current to see how we're doing. And it also has two buttons that can send CAN information. All of this is receiving data through the CAN bus, mostly from SCADA, but these buttons will allow you to send messages as well.
As well as being the project manager, I also was responsible for the cooling design. I sort of headed the electrical part of this. I wanted to make a completely removable cooling enclosure that would be placed on the car and could be placed anywhere on the car, but in a specific location I had in mind on the back of the car above Carman. With the new motor that we got this semester, we needed to dissipate more heat in the system, so we needed a new cooling system essentially. We were not handed down the best cooling designs from last year, but luckily we were able to design this and actually get something manufactured at least this year without this cooling system.
The new motor that last year's team selects, the MRAX 208, as pictured here. This was chosen over the previous motor because of its high power output and as well as its weight savings.
One of the big advantages of this motor, though, is because it's so small, the entire drivetrain assembly can be put together outside the car and installed in one piece, which is really nice.
Yeah, our motor's pretty cool.
It's a super cool motor.
Thanks, guys.
I'm very happy with it.
My name is Montserrat. This is the motor controller. This was the design that was finalized. We wanted to have a rules compliant strain relief enclosure, as well as make sure the cables were well organized. We wanted to make sure that it was cost efficient, it was easy to fabricate, and it was water resistant as well, because that's a key feature to note. This was made out of three main parts. There is a shell, a lid, and a mounting plate, all made out of aluminum. However, sadly, due to our current situation, all parts were made, but it was never put together.
Back to the relay board, this sits in Carman and relays voltage from the TSV battery packs to the motor. So this is completely manufactured. The only other thing that would need to be added to this would be insulative paint and then some more testing once the IMD and TSI systems are finished.
So for the SCADA system, provides the control and data acquisition system. It is a system that monitors the other electrical subsystems of the car, such as the TSI, GLV, the packs, and based off the data that it's receiving, it stores it for the user to be able to see or witness how the car has been running overall, as well as it responds to situations that it may see, such as like overheating in the motor controller or other signals that the data is out of the chart, out of the expected values. And based off that, it can shut down the car through the SCADA relay or the motor controller if need be.
So what you're looking at is a diagram of the current system. It sort of was an experimental thing, but we wanted to focus on making it much more modular and a lot simpler. We were able to, I think, achieve a lot of that, especially the work Troy and I did this semester while we were away. Let us focus a lot on software.
Hi everyone, my name is Troy. I'm a junior EC, and I was working on making a post-processing tool for SCADA, as Connor was mentioning, and I just want to go into a little bit about motivation for making the post-processing tool, which we called the Lafayette Electric Race Car Data Analysis Tool, or LERDOT. Previous years, the SCADA system always stores information for the sensors, and it was previously storing all of this data in a SQL database, but that was the extent of it. So if you ever wanted to actually look at the data, it wasn't really possible. So I wanted to create a tool that allowed for easy access of the SCADA data.
Okay, so I'm Luke. I'm the other member of the drivetrain team, and I'll talk a little bit about what we accomplished last year. So basically, we started by inheriting an old motor and mounting system from last year's team. Last year's team based this off of an older motor, so we got a new one. So a lot of changes need to be made. And we also realized at the beginning that a lot of the mounting system had a lot of things that weren't rules compliant. The first thing we wanted to address was making sure that everything we designed was rules compliant. We think we accomplished that by making sure that everything was set up for a safety wire or had lock nuts on them. In addition, we also needed to make sure that we passed the rain test, which is something that they did not do last year. So to do that, we created a waterproof housing for the motor and cable connections. We also needed to redesign the mounting system. We realized that it wasn't perfectly, structurally sound. So we beefed up the mounting plates for the new motor, which is kind of what Michael talked about earlier. At the end of the semester, before we all left, we had basically an assembled drivetrain, which you can see in the picture here. We were able to get it in the car, which is really exciting. So we think next year's team's going to be in a pretty good spot.
All right, so my name is Dan Becker. I worked on the suspension team with my two teammates, Carl and Zach. This was kind of where the car was at in terms of CAD design. That's where the car was at when we left, what we accomplished throughout the year. We basically started from scratch. The previous team had given us some parts. They gave us like one A-arm and a couple push rods, but their design wasn't very good, and it built off of previous year's designs that had problems regarding spherical bearing failures in the A-arm or in the ends of the A-arms where they attach the uprights. So we decided to just start from scratch and completely redesign the A-arms, uprights, push rods, bell cranks, and all the mounts associated with everything. It was a pretty big task, but right before we left for spring break and before all of the coronavirus stuff happened, we actually got the car on the ground for the first time. So that was a pretty huge accomplishment for us.
Again, my name is Zach. In addition to being on the suspension team, I also was the steering system designer for this year's project. So it's fairly self-explanatory for most people, but in case you don't have a general idea, suspension is in charge of making sure that the car is stable and sitting well on the ground, whereas steering is making sure that the car is pointed in the direction that we want it pointed in. As far as accomplishments for this year's steering team, we basically redesigned from the ground up the steering system as a whole. This included new front and rear control arms.
All right, so I also worked on pedals this year. It's a pretty small subsystem, but there was a decent bit that got done in the short time that I had to work on it. So my major accomplishments were that I nearly finished the entire pedal box in the time that I worked on it.
All right, well, hello everyone. I'm Gabe, and on the chassis team. So we had gotten a chassis from last year's team. Unfortunately, a lot of it wasn't rules compliant, so we had to make some pretty major changes. The first one of these is widening the cockpit area. It's about an inch too narrow, and so we decided to cut out the side impact members and redesign them. Another one was redesigning the battery boxes on the side of the car. The ones that last year's team had designed were too big. We also had a problem with ground clearance, and we had to change your suspension. Yeah, so most of the work that we did was just modifying the chassis to make it rules compliant.
Thanks, Gabe. I just kind of went into what the cooling was before, but now I want Phil to talk about what makes it so cool.
Thanks, Jordan. So before I go into the car design, top left corner, you can kind of see some components from the old design. There's been various cooling components used throughout the years. And so this year, the plan was to use a bigger radiator to dissipate more heat. We needed a big overhaul this semester.
Yeah, thanks, Phil.
So here is a technical top-level full car electrical system diagram. Throughout the whole project, it was essential to keep an updated system as it acted as a guide for all the members of the team, so everyone is on the same page, and it also functions as a manual for how to piece the car together. Shown here is all the different electrical subsystems which were previously talked about in this presentation and how they work together. I wanted to give a more simple, brief overview of the car as a whole. So there's the battery packs, which supply voltage to the vehicle through the relay board located in Carman's high voltage region, which creates a current path to the motor controller, and then the motor controller powers the motor. The TSI subsystem interfaces between the high voltage and the drive state of the car by taking high voltage and current measurements, as well as interfacing with pedals, and provides other signals to the cockpit. And it also takes temperature and flow measurements from the cooling system. And then the cooling system is powered by the GLV battery through the breakout board to a DC to DC converter. The GLV battery also powers all other low voltage systems in the vehicle through the breakout board, which is in Carman. And then GLV also measures low voltage and current, as well as being the brain behind the safety loop. And then there's also SCADA system, which communicates with major subsystems through the CAN bus. So yeah, that's a brief overview of interconnect and the whole functionality of the car.
I also want to testify to how important this document was. Both semesters we had a giant printout of this document. We were just using it to understand all the connections, and it was just phenomenal. This document should be held in really high regard for next year's team. But yeah, that was our presentation. This is essentially our last time as a class meeting together. So I really thank you guys for stopping by.
I'm going to talk a little bit about some takeaways from this project. This is a really great opportunity. You'll probably learn more on this project than you have in any other class. So if you like design, if you like CADing something, if you like manufacturing it and then building it, this is the project for you.
In working together, there was a huge takeaway because just collaborating with your peers allows you to learn a lot. It's a great process to go through, and this project provides the perfect platform for that.
My main takeaways from this year, as someone who recently shaved their head because they got bored of their hair, I can tell you that you're going to make mistakes, but you just got to own up to those mistakes, live with them, learn from them. Don't be afraid to make more mistakes because you're going to.
My takeaway from this project is almost nothing you do will come out right the first time. That's kind of the whole point of design, is that you iterate and find ways that things work and find ways that things don't work, and that's all part of the process, and you shouldn't let that discourage you.
So the biggest takeaway from this project was the fact that this project was interdisciplinary. Most engineers typically stay in their little bubble, and so I thought it was really cool that this project allowed us to expand and work very closely with electrical engineers, because we were able to bounce off ideas and take things into consideration that we as mechies probably never even noticed. And then this project just created a lot of new friendships, so that was nice.
My takeaway from this project is that making design choices can be scary. There's not a way for you to avoid it. The only way that you can build a car that works and functions is to not be afraid.
Definitely my biggest takeaways from this project was the ability to work effectively in a large group setting. Learning to be able to admit mistakes, help others, meet deadlines, and be transparent with my peers are all valuable skills that were definitely strengthened throughout the project.
You're going to be able to do the things that you're learning as you go, but the things you're good at, take pride in them.
So I'd say my biggest takeaways from the whole project is that there's a lot to learn and not enough time to do it. So if you're excited to learn, be ready to learn. It made the whole thing a lot more exciting and rewarding at the end.
My biggest takeaway from this project is just the knowledge and experience I've gained just working on this thing, and just how far this team has come. It's really amazing.
The biggest impact I had from this project was the amount of work that goes into it. It's very, very challenging, but it's also very, very fun. And by the end of the year, you'll be very proud with the Formula car you guys make.
I'm just going to talk a little bit about some advice for this project. So the biggest one is jump headfirst into this project.
Just start everything early and earlier than you think you need to start it.
Stay organized, keep the lab clean. It can suck, but once it gets bad, it's real bad.
Always document your design, always document your data, and always make comments in your code.
Not give up on the systems that were created this year.
I feel the first step to a successful project will be proper planning.
You should be concerned about subsystems other than your own. Work as a team.
Listen to what other people have to say.
Know that you're not alone.
Take a step back when things are getting tough or you have a lot of work. Just realize you guys are all working towards a common goal.
No matter what you're doing, just be proud of the work that you do.
Make sure you become friends with the people on this team.
And the people from the past, including us, are counting on you. Don't make the project your life. Enjoy your time. Enjoy your senior year, but make a badass car. Yeah.
Maybe you could fly my kite.